right. Thank you, Denise, for the kind introduction. And I'd also like to thank the Academy for inviting me to speak here tonight. This is a real pleasure for me to tell you a little bit about the work that my group is doing at the university. Okay, so I'd like to start with some acknowledgements. The work that I'm going to present tonight is funded by the United States Department of Energy. And I would also like to thank Sandia National Laboratories, where I worked for about 10 years before I came back to Missouri to take an academic position. And I would also like to thank UMSL for providing the laboratory space and giving me the opportunity to come back to the Midwest and do some science here. So if you have any questions during the talk, please stop and ask. I would be more than happy to talk answer any questions that I can going forward. Okay, so what does nanoscale mean? I'm sorry if it's kind of hard to see the graph on the left here, but a nanometer is it's 10 to the minus 9 meters. It's a billionth of a meter. And an atom is about a tenth of a nanometer. So that's a very small object. Computer integrated circuit lines are about 10 nanometers. You may have heard this when people discuss their computer chips and what process Intel and AMD and those companies are using to prepare their chips. And to give you a comparison, a human hair is about 80,000 nanometers, so it's quite large on this scale. Nanometer scale materials have much different properties than what we call bulk materials. So if I were to take a piece of metal out of the laser pointer here, and it's a fairly large piece of material, but if I could carve it down to a very, very tiny piece of material that was on the nanoscale, the properties of that material would be much different than what we see in bulk. And just to give you some examples, you can change things like the melting points of materials to a large degree if you get them very small. You certainly change their interaction with other high surface area materials, and this is the interface energies. And I'll tell you more about this as we go on. So what we're trying to do largely here is control the size, the shape, and the chemical composition of materials at the nanoscale. And that allows us to really tune the properties of materials to things that are more useful for our applications. Okay, so let me give you a specific example of an area where we're applying technology to try to make some advances in things like transportation. So these numbers that I show here on the slide are taken from 2015. So transportation in the United States, we use about 380 million gallons of gasoline per day. And the total here is about 9 million barrels per day, which is quite a large number. And we would like to be able to maybe not so reliant on petroleum for our transportation needs. We do have two alternatives, and those alternatives include things like hydrogen fuel cells, which I'll talk more about tonight, mostly about tonight, and also electrochemical batteries. And batteries now are pretty well into the commercial market space. The Prius and other electric vehicles or electric hybrid vehicles are now around and pretty prevalent. When it comes to hydrogen fuel cells, there are some specific advantages that make us want to, or would tend to make us want to go in that direction. They're very efficient with regard to their energy use. So when we try to convert energy from one form to another, so for example, chemical energy to the translational motion of a vehicle, for example, some systems are more efficient than others. And fuel cells are about 60 to 90% efficient in this regard. And combustion engines, by comparison, are only about 25% efficient. So it would really pay to go to this new technology if we can develop it. In addition, with a fuel cell, a hydrogen fuel cell in particular, there's no carbon emissions. And so we can eliminate our carbon footprint for transportation. Okay, so why hydrogen? I'm showing here a chemical reaction in which I take a hydrogen molecule and I split it into a water molecule, and I split it into hydrogen and oxygen. This chemical reaction is very simple, and it's also reversible. And it's a carbon-free energy cycle. So this is something that's of importance to us. So hydrogen is an energy carrier. It's much like electricity. Electricity we have to produce. We can't just pump it out of the ground like we do oil, for example. So we call it an energy carrier. And the way that we can produce hydrogen from water is simply electrolysis of water. So we split the water, and I'll show you that process in just a moment. Another method that's being used at the moment is steam reforming of hydrocarbons. This is currently the commercial, this is the current commercial process, which is not actually, it's not actually a clean process. It produces carbon, and so we would like to move to different methods of production. Once we are able to produce the hydrogen, we would like to store it in some way so that we can use it on an automobile, for example. So we can either store it as a gas, or we can store it as a liquid, or we can store it as some kind of a chemical compound. And once we have the hydrogen on a vehicle, for example, you can actually burn hydrogen in an internal combustion engine that you currently have in your vehicles. And this has been known for quite some time, but it's not as efficient, again, because it's an internal combustion process. And so we would really like to move to fuel cells in order to utilize that hydrogen. Okay, so how do we produce the hydrogen? And I mentioned electrolysis earlier. So what I'm showing here in the left figure is just a simple battery that you could buy at any store. And then this is just a pool of water, and I have two upside-down test tubes in the water. And I take one electrode and I put it up into one upside-down test tube, and I take the other electrode and put it on the other test tube. And if the voltage is high enough, the water simply splits, and then the gases collect in the top of the test tubes. Here we have oxygen on one side and hydrogen on the other. So all we really need to do to produce hydrogen cleanly is simply to use other resources here that we have that are renewable. So for example, wind and solar, or even hydrothermal. Any of these methods would be adequate to produce hydrogen for our purposes. Now, the Department of Energy has, as a country, we have a lot of things we need to think about if we're going to move to a new technology. The energy infrastructure is expensive to change. So if right now we're all filling up our automobiles with gasoline, and if you go to a station anywhere in the country, essentially everything is the same. The pump handles are mostly the same, and so on. So you can imagine that if we're going to change to a new kind of technology, say hydrogen storage for fuel cell vehicles or electric vehicles, we have to have standardized technology at each of these filling stations in order to make this a reality across the country. And so that's a very expensive proposition. So what the Department of Energy likes to do is try to organize this and help American industry to coalesce around different ideas, and in the hopes that the transition is as smooth as possible, and that the correct technology is possible and is fieldable. And so this incorporates a large number of different things around this wheel here that I'm showing. So there's production, there's delivery of the hydrogen once you produce it, there's fuel cells in which you utilize it, there's the storage aspect, which I'll talk about tonight. There's education and codes and standards and safety, so we want everybody to be able to fill up their vehicles safely. And hydrogen is not without its safety issues, but those are largely addressable through engineering and other means. Okay, so the term given to this is the hydrogen economy. Maybe some of you have heard of it. So when in the future, as we move away from petroleum and fossil fuels, we're going to tend more toward this hydrogen economy, and the use of hydrogen for our energy purposes will become more prevalent, and that's the name given to this process. Okay, so I want to give you some numbers that you can think about as far as if we're transferring to a new technology, what are the difficulties in doing so. So I'm showing now energy densities of materials, some of which you're familiar with, and I'm giving them in terms of the energy per liter. So you all know about how much volume a liter takes up, and I'm giving the energy here in megajoules. So gasoline is at the top of the list here. It has about 34 megajoules per liter, which is quite a large number. If you consider the lead-acid battery that you use to start your vehicle, per liter it has an energy density of only about 0.6 megajoules per liter. Lithium-ion is several times higher than the lead-acid battery. That's why lithium-ion technology is of interest for electric vehicles. And then we can move on to hydrogen to see how well hydrogen compares to gasoline. So hydrogen gas, hydrogen is normally a gas at standard temperature and pressure, but you can compress it, you can liquefy it, you can have it in several different forms. Hydrogen gas at a very high pressure, so 700 bars, about 700 atmospheres. So this is a very high pressure gas. Has an energy density of about 6 megajoules per liter. And if I cool that hydrogen to a very, very low temperature and actually solidify it so that it's much higher, it's higher density, I can get up to about 12 megajoules per liter. And you can see by comparing this to the energy density in gasoline, we're still quite a bit away from gasoline's energy density. Yes?
What temperature would you need to cool the hydrogen down to in order to make it a solid? Do you know that off the top of your head?
Around 4 kelvins. Wow. Very, very low. It's very hard to do. Gasoline is difficult to compete with because gasoline is a hydrocarbon. We burn the hydrogen when we combust gasoline. We also burn all of the carbon, which is what produces the CO2 emissions from gasoline. But it's a very energy-rich material, and so it's difficult to compete with that number. So what we try to do is pack the hydrogen even more densely than we can in a solid. And so in addition to, well, instead of cooling it, I should say, into solid hydrogen, we can actually combine it with different metals, for example, or other chemical compounds, and we can actually get a higher density of hydrogen than we can in a solid. So I'm showing here magnesium hydride, which is a popular material for hydrogen storage researchers. And if I look only at the hydrogen density in magnesium hydride, this is a solid, you could hold it in your hand, it's got a higher energy density than even solid hydrogen. So this is the direction that essentially we're moving in terms of hydrogen storage on vehicles. Okay, so this is a picture of 3 what are called fuel cell stacks. So these are the actual apparatus here that will convert the hydrogen and oxygen from the atmosphere into electricity for your vehicle. So the large cell here is about a 5 kilowatt cell. So to propel your car, you'll probably, I think there are around 10 kilowatts that go into automobiles that are fuel cell vehicles. And then there's some smaller ones here just to show you what kind of they look like. Okay, so the principle behind the hydrogen fuel cell is really very simple. So on the left-hand side here, I'm showing separated hydrogen gas and separated oxygen. And I've got a scale here on the left that goes from a vertical scale here, so that the energy is higher as we go up on the scale. And when hydrogen and oxygen are separated, they're in sort of a high energy state. And in order to lower their energy, and everything wants to lower its energy, you can think of a ball wanting to roll downhill, it wants to lower its energy. The hydrogen and the oxygen would like to combine and lower their energy because the H2O molecule is a low energy state. And so the principle of a hydrogen fuel cell is to do this in a controlled fashion. We want to combine the hydrogen and the oxygen in a way that they don't react too violently or too vigorously. So a fuel cell is composed, a hydrogen fuel cell is composed of a membrane layer, and the membrane layer will only pass protons. So a hydrogen molecule that comes to the surface of the membrane will dissociate into protons and electrons, and that's done by a chemical catalyst on the surface of the membrane. On the other side of the membrane, we place oxygen. And oxygen also dissociates on the surface of the membrane. And when the protons migrate through to meet the oxygen, they'll start to react with it. But the electrons can't get across this membrane. But they really want to be there. Electrical forces are very strong. And so the electrons have to find a path to get around the membrane in order to rejoin and form the water molecule. And this process is done through, it's the electrons that do the work here. We go through an external circuit, and the electrons do the work as they go through that circuit. So you can think of this proton exchange membrane, or this fuel cell membrane. It's essentially a battery, except we keep adding the reactants on the left side and the right side. But it operates in a fairly similar way. Okay, so how do we actually store the hydrogen? And this is going to be one of the primary areas of the talk here. And I mentioned a few physical-based means already. So we can compress the gas at room temperature, or we can cold cryocompress it at lower temperature, or we can go all the way and try to liquefy the gas. And these are all technologies that have been developed. And in fact, if you buy a fuel cell vehicle, you can buy some test vehicles that are on the market now in California, where they have hydrogen fueling stations. And what you'll purchase is actually a compressed gas system. And you'll have to go to a filling station, and it fills up your tank at a pressure of 700 bar, which is quite high. The other method for storing hydrogen is material-based, and this is where a lot of the material science comes in. And so there are things called adsorbent materials, and these are very high surface area materials that might have surface areas as high as 8,000 or 10,000 square meters per gram. So you can imagine a basketball court or two in the palm of your hand, or several basketball courts. These materials don't take up too much volume. Liquid organics are another method. Interstitial hydrides, and I'll tell you a little bit about more of these in just a moment. And then there are the complex hydrides, which is the focus of my talk tonight. And then there are some other materials called chemical hydrides. Yes?
Are the material-based, are they ambient temperature?
Good question. They operate over a variety of temperatures, and that really depends on the material property. So some of them are fairly ambient temperature, but some of them are very, very high temperature materials as well. And so controlling those aspects, those temperatures, is a large part of the current research thrust. Okay, to give you an idea how, another reason we want to go away from a compressed gas or liquid tanks is simply, this is something that the automobile manufacturers would like for the purposes of having more space on the vehicle and so on. So this is the trunk of an automobile that has a high pressure compressed gas tank. And these tanks aren't made out of steel, they're made out of carbon fiber. But nonetheless, they're still quite bulky, and so you can see that it takes up essentially the entire trunk space of the vehicle here. What I'm showing here are liquid hydrogen tanks. And these tanks are sophisticated in the sense that you have to have lots of insulation, and there's lots of electrical controls here to try to regulate things within the tank. And so there's an extra sophistication and cost that goes into liquid hydrogen tanks. Okay, so I mentioned a couple of the other materials based storage approaches. And there are two that are very successful low pressure hydrogen storage approaches. So in this instance here, we can store the hydrogen at fairly low pressure, so around atmosphere, maybe 1 atmosphere, maybe 2 atmospheres. And one of them are these physisorption materials for molecular H2 that I mentioned earlier. So these are the high surface area materials that have 10,000 square meters per gram, for example. And some of these materials are called metal organic frameworks. Those are the most popular ones at the moment. And the way hydrogen is stored on a material like this is not unlike dew forming on the grass. So at night, when the air temperature gets cooler and the temperature drops, a lot of times you'll see condensation of the water vapor that's in the air on things like grass blades. And it's a very similar mechanism that causes the hydrogen in the gas phase. If it's low temperature enough, it will stick to the surface and condense onto the surface. And that's one popular method that's being really explored today. And then the area that I'll tell you more about tonight are compound hydrides. And so these are things like the magnesium hydride that I mentioned earlier, and also other compounds. This is a picture of a crystal structure of lithium borohydride, where we have These yellow atoms are lithium, and then we have boron atoms that are in green, and then hydrogen atoms that are in this brownish color. Okay, so how much hydrogen do you have to have on your vehicle in order to utilize your vehicle the way you'd normally use a gasoline engine vehicle? And the targets here are given essentially, they're determined by the Department of Energy. They were set by the Department of Energy and the automobile manufacturers. And the goal here is to have a range of about 300 miles. And another important factor here is the cost that's comparable to gasoline to reach these targets. So the system parameters that we have to match here are cost. We have to have a fairly dense material, but it can't be too heavy. And we also can't take up too much volume. And in order to get this 300-mile range, it requires about 5 to 8 kilograms of hydrogen on the vehicle, which is a pretty large number, actually. But it is a number that's achievable with the metal hydrides that I've mentioned before. All right, so let's look at some common metal hydrides. If you look at the periodic table, many elements in the periodic table will form compounds with hydride, with hydrogen directly, if you simply raise the temperature and let them interact. And they're classified into several different regions, so I'll give you a couple of the names here. So if we look at the alkali and alkaline earth elements, these are things on the far left side of the table, the first two columns. They form what are called ionic hydrides. So these are either for the alkali elements, they're monohydrides, so sodium hydride and lithium hydride. And if the metal has 2 electrons, it's called a divalent metal, like calcium or magnesium, they form dihydrides, so calcium H2 and magnesium H2. In the middle of the periodic table are what are called the transition metal hydrides. Some of these are big heavy metals like palladium, but other lighter metals like titanium and vanadium also form hydrides. So these are called the metallic hydrides because they are actually metallic. They could flow a current through them. And these are the most well-studied hydrides for applications purposes. And among the metal hydrides, the metallic metal hydrides, 2 classes sort of stand out as being have already been commercialized for various purposes. They are called AB2 hydrides because you have metals A1 and B2 of the Bs. And then there are AB5 materials like lanthanum nickel 5, where lanthanum is A and nickel is B. And I'd like to point out that lanthanum nickel 5 was actually, it can be used also as a battery material. And lanthanum nickel 5 batteries were in our cell phones and our laptops before lithium ion came in and took over the market. And in fact, the first Priuses were based on these AB5 type alloys. So I'm not sure if the Priuses might have gone to lithium ion now, but they started out as metal hydride batteries, in fact.
Yeah.
Yes?
How did you get H0.6? Like how is there not a full hydrogen atom? Or H4.14, like where did the...
That's a very good question. So sometimes when you're putting hydrogen into a metal, the electrons, this is a bit of a technical question, but the electrons don't necessarily want to go in from the hydrogen. So the proton will still like to go in, but the electrons have to go to a higher energy state, and so they'll stop at some particular composition. Good question. Okay, we can take some of these elemental hydrides, and I'll give you 2 examples, aluminum hydride and lithium hydride, and we can react them to form what are called complex hydrides. So if you look at aluminum hydride, it looks basically like table salt if you looked at it close up, and so does lithium hydride. And we can simply react these materials and form another compound called lithium aluminum hydride. And the properties of lithium aluminum hydride are very different from either aluminum hydride or lithium hydride separately. And so it's mixing and matching these different hydrides and making complex hydrides that has been a driving force for much of the research of the past 15, 20 years, and has led to a lot of new materials discovery, but we're still searching for that ultimate material that has the properties that are useful for use on an automobile. Okay, so this is maybe the most technical slide that that I'm going to try to explain. So there's an important property of metal hydrides for engineering purposes that's necessary in order to have the properties that you would like that make a metal hydride useful. So I mentioned the fuel cells, these hydrogen fuel cells like to operate at a pressure of around 1 atmosphere. And so you want your hydride material that you have in some kind of a tank or a bed, they call it, you'll have to heat it a little bit to get the hydrogen out, and you want that hydrogen coming out of your material to be around an atmosphere. You don't want it to be really high pressure, and you don't want it to be really low pressure. You want it to be right around an atmosphere because it's easy to regulate, and it's easy on the fuel cell, and it's easy to engineer around that pressure. So there's a material property that's called the equilibrium pressure in any metal hydride. And so this is how we measure this so-called pressure composition isotherm, which gives us this, this pressure. So I've drawn a graph here on the lower left corner. So I have hydrogen concentration in my sample, and I can simply denote that as H over M. So this is the ratio of hydrogen atoms to metal atoms. And on the y-axis, I have the hydrogen pressure. So imagine that I have a box. This is your fixed tank. It's a fixed volume tank, and I have some material inside there that's going to react with my hydrogen. So what I do is I introduce a small aliquot, or just a small, very definite puff of gas that I know I know the quantity that I've introduced into the tank. And if I introduce just puff after puff after puff of hydrogen into the tank, and I let it sit for a long period of time, it will come into equilibrium with whatever my sample material is down here, that reacts with the hydrogen. And this is chemical equilibrium, and this is how we denote it. We say that the chemical equilibrium, we say that the hydrogen in the gas is in equilibrium with the hydrogen in the solid. And this just takes time. It depends. It's different for different materials. So as I introduce the hydrogen into the material, I'm increasing the hydrogen concentration. So I'm going from left to right here on my x-axis. And eventually, I'll see the pressure go up when I introduce this gas. And as I keep introducing it until it reaches what's some kind of a saturation point. And at that point, it starts to react strongly with the material that's in the tank. And at that point, the pressure plateaus. And I have a flat pressure curve here. And this is a material property that's of importance that I mentioned before. And the pressure that you get here at a particular temperature is what's characteristic of the metal in the tank, or of the material in the tank. Okay, so these pressure composition isotherms are very temperature dependent. So if I increase the temperature, so if this were the pressure plateau at some temperature T0, if I increase the temperature, the pressure will raise significantly. And if I lower the temperature, it will also drop. And from these different temperature pressure plateaus, we can extract an important property of the material, which is called the enthalpy. And enthalpy is a measure of how much heat is required for us to either put in or take out of the material in order to have the reaction go backwards or forwards. So I'm showing here a simple chemical reaction. So I have metal HX, so metal hydride goes to metal plus some number of gas hydrogen molecules. And with that reaction, there is a corresponding enthalpy or heat of reaction. And it depends whether you go forward or backward. Okay. Okay, so let me tell you about another very well-studied complex hydride. This is called sodium aluminum hydride. So I have 1 sodium, 1 aluminum, and 4 hydrogen atoms. And this material is of interest because it happens to have a plateau pressure right around an atmosphere, depending on what temperature you're at. The problem with this particular material is that when you decompose it, it's not very simple. It undergoes 2 very complicated reactions. And all these reactions that I'm showing here are chemical reactions. I transform this sodium aluminum hydride that has 1 sodium, 1 aluminum, and 4 hydrogens into another solid compound that's got 3 sodiums, 1 aluminum, and 6 hydrogens. And in addition to that, a little bit of aluminum gets away. And that's problematic because it's very hard to reverse these reactions and go back. So if you have this material in the tank of your car and you want to go back and plug in your high pressure hydrogen hose and reform the material, that presents a lot of problems for us. Not only is this reaction complicated, but it's also only half of the reaction. So the other half of the reaction is if we get the material a little bit hotter, then this sodium 3 aluminum H6 will further decompose into sodium hydride. That's another simple monohydride, and it will segregate more aluminum, and you'll get some hydrogen off of it. So we have two separate reactions. And this is problematic if you're engineering a hydrogen tank, because then you have to deal with the tank at two different temperatures, and in addition to all of the materials problems of going back and reversing from this. So if your tank is completely depleted, this is all you have in it. You have sodium hydride and aluminum, and you have to try to rehydrate that material and go back both of these reactions. So the figure on the right here is just the PCT curves, or pressure composition isotherm curves, for these two reactions. And that's why you see two plateaus here. There's one plateau for one reaction and one plateau for the top reaction.
How different
Yes?
are the temperatures?
I'm sorry?
How different are the temperatures for the first
Well, so I mean, you can run the reaction at a given temperature. So for example, these curves here are for 199 degrees centigrade. So when you start decomposing the material, you'll go through this first reaction, and then the pressure drops dramatically, and then you go through the second reaction down here, and that's all both at 199 C. So, but they did these measurements at a variety of different temperatures to calculate these enthalpies of reaction.
What is the danger level on using hydrogen cells?
That's a very good question. So these materials are typically very reactive. If the materials are exposed to water and oxygen in the atmosphere, they'll typically catch on fire quickly. But there are ways to mitigate those safety issues. So while the materials themselves have some issues with safety, I'll describe a little bit later here how we can get around those issues. Basically, if we just keep the oxygen and water away from the material by enclosing it into in something, then we can largely mitigate those issues. Okay, so the current state of the art, a colleague of mine and I wrote an article for the MRS Bulletin a few years ago. And despite the large amount of research that's gone into this area, we haven't found a magic material that has all the properties that meet the DOE targets and is easily reversible and whatnot. So the community, the research community as a whole, has been moving toward a couple of different approaches to try to solve the issue. And so that brings me to the focus of having nanoscale materials in material science, in particular this particular area. So again, I want to go back to this notion of nanomaterials having much different properties. And what I'm showing here are two crystals, or cartoons of crystals, for example. And I want you to focus on the left crystal here at the atom that's in the center of this green circle. So if this atom has 1, 2, 3, 4, 5, 6, 7, 8 neighbors. And so if this atom is in bulk, it's pretty happy there. And there are more atoms in the bulk than there are on the surface for a very large material. On the other hand, if I look at a particular surface atom, in this case, I have 1, 2, 3, 4, 5 neighbors for this surface atom, and in this surface atom, I only have 3. So the point here is that if you're on the surface, you have less neighbors than you do if you're inside the bulk of the material. And that means you're bonding differently. You don't have as many bonds, for example, in the surface atoms that you will have if you're in the interior of the bulk. And that lack of bonding to the other atoms changes the surface energy of the material quite dramatically. And so these atoms that are on the surface would really probably rather be on the interior most of the time. And so we can utilize that to to control a lot of the properties of the material if we can take it down to the really small nanoscale size. So the two primary effects that dominate at the nanoscale are shown in the box here. And what I want to point out here is that if you try, you can quantify this fairly easily. If I have if an atom is about a distance a away from another atom in a particular solid, I can calculate the ratio of the number of atoms on the surface to the total number of atoms in the sphere here. It's given by essentially 1 over the radius. So as I drop the radius of the nanoparticle, the number of atoms on the surface goes up very quickly as I get very small. And what that means that the surface here contains most of the atoms, and then I have two things that then dominate the properties of this little nanoparticle. One is that surface energy I mentioned earlier, and we can utilize those surface energies to do things like lower reaction enthalpies or make things more reactive and so on. And the second property is that particle surface interaction is very important here. So there's no such thing as a true free nanoparticle because it's always in touch with something else. You can never have a truly free nanoparticle. It's always in contact with some kind of a surface somewhere. And what I've shown here on the bottom of the slide is this black mass here is essentially is carbon. And I'm going to show you what we make in our laboratory, which are carbon frameworks. And in our carbon frameworks, there's a lot of surface area, so there's a lot of little ridges and edges in our carbons. And in those little spaces and ridges, we put nanoparticles, and those nanoparticles are then in contact with these carbon materials, and that allows us to really change the properties of these hydrides. So this is some work that I did a number of years ago with some collaborators at Sandia National Laboratories, and what we were trying to do was really go to the small scales and look at the range of effects that we get as we can control the size definitively of these nanoparticles. And so for that, what we need are well-controlled, what are called nano frameworks, in order to put our materials into. So the idea here is that we have some kind of a rigid structure, and we can control the pore size of the structure. And inside the pores, then we can put these metal hydrides and look at the effect of changing the size. One, and the other effect is how do they interact with whatever framework we're using. And so my colleagues at Sandia, were looking at metal organic frameworks, and these have very small pore sizes of the order of 10 angstroms to 20 angstroms. And my group was looking at carbons that had anywhere from 20 angstroms and on up in size, pore sizes. Okay, so to give you a little bit more detail about what we're looking at or looking for, I want to talk about another complex hydride, which is lithium borohydride. So this is very similar to sodium aluminum hydride, except I just go up one in the periodic table for both aluminum and sodium. So I go up to lithium, and then I go up to boron. So this material has a large amount of hydrogen, and it binds it very tightly. But it would be great to use as a material because it's so high energy, its energy density is so large. When we decompose this material by getting it hot, we have several different reaction pathways that we can follow. And in particular, in bulk, one of the reaction pathways that we know is followed is that we go from lithium borohydride to lithium hydride, and we get this compound B2H6. This is a compound called diborane, and it also comes off of the material. Unfortunately, diborane is bad for two reasons. One, it's a gas, and if it escapes the system, some of our active material is gone, and so we can't rehydrate it. And the other problem is that diborane is a toxic gas, and so we don't want that to be released at all. Okay, so how can we utilize some of these materials that we're making to control some of these reaction pathways? And maybe we can utilize some of these other reaction pathways. So in order to make some of these framework materials that I mentioned earlier, we use a chemical process, and this is a process that we actually didn't invent. It was invented by Meng and coworkers in 2006, and we've been using and modifying this process for a number of years. But I'll just describe the basic idea here. So everyone knows that oil and water don't mix, right? And we can utilize this notion that things don't want to mix in order to make nanoscale structures. And the way that we do that is we have materials that are, have a fixed size, and so we'll use things like polymers. We can control the chain length of polymers very accurately. And we can make polymers that don't want to mix with other materials. And so in this particular case, we make something called Resol, which is it's a phenolic resin. It's not important. The details are not important here. But this resin does not necessarily want to mix with all portions of the polymer that we're going to put inside it. And so when we mix these materials together, we do it in an ethanol bath. So this is just an alcohol bath. They mix, and then when we dry the material, we just evaporate the ethanol off. These materials, they'll segregate, sort of like oil and water likes to segregate, except they'll do it on a very, very small scale, and they'll do it on the nanoscale, in fact. And so what one is left with here is a composite that has a nanostructure. And so the pores here, I'm showing some pores here in this little hexagonally packed cylindrical pores. These pores can be made anywhere from 2 nanometers to 10 nanometers, say. So with this material, there's a lot of stuff in here at the moment because we haven't gotten it hot yet. But we can simply put the material now into an oven, and we can bake it until we just cook everything off, except we leave only the carbon. And to do this, you have to go to temperatures anywhere from 600 to 1,000 degrees centigrade, which is very hot. But it leaves you with a very clean, porous network or framework. And so the one I'll focus on here is this hexagonal one. So you can see that these are little cylindrical pores, and they're packed in a hexagonal fashion, if you will. So they're little tiny tubes, basically, in a carbon mass. Okay, and this is the production process. This was my postdoc, Zhengfang Liu, who did a lot of the work a number of years ago. And you can see when we put the material into, he's just put the material into petri dishes. This is when it's not been through the oven yet, so to speak, and so it's kind of floppy, and you can manipulate it with your hands. And then this is just a very high temperature oven, and when you get to the end of the process, you are left with just a very fine carbon powder. But the powder has this very particular microstructure. So if we look at the microstructure with an electron microscope, which is a very high powerful microscope, we can see very fine details. And so there's a scale bar here on the left that's 40 nanometers. And what you're seeing here, these bright spots are actually the holes in the carbon. So if we look down at the surface from the top, you can see this little hexagonal pattern. These are the little pores that have arranged themselves. And then if we take that material and we tip it sideways, we can see the pores running through the carbon, and you can see how uniform they are. And I should also mention in passing here that the surface area of these carbons can be as high as several thousand square meters per gram. So on the scale of high surface area materials, it's sort of mediocre, but we are looking more at the interior pore volume rather than just the surface area of our materials. Okay, so what happens if we put one of these complex hydrides into one of these nano framework materials? And I mentioned earlier lithium borohydride. So lithium borohydride is a solid, and you can melt it at fairly low temperature. And if you melt it in the presence of these nanoporous carbons, they just suck up into the carbons. It wicks up into the carbons. So another way to say that, more technically, is that it wets the carbon. And so we can put the material in these little frameworks, and then we can go ahead and decompose it, and we can look at what kind of gases come off. So we can look at the reaction pathway for the material. So what I'm showing here is a graph. We can detect very specific gases. And in this particular case, we're looking at the production of B2H6, which is the diborane gas. And on the x-axis is the temperature as we get the material hotter and hotter. And what I've shown here in black, red, and blue are the different pore size materials. So blue here is a very large pore size material. It's about 15 nanometers. And you can see a very definite blue peak here. So this is the diborane that comes off at around 350 degrees centigrade. In red, we have another carbon that's only 9 nanometers, so we're going to smaller pore size. And you can see that the diborane drops significantly. And as we go to a 4 nanometer carbon, in black, the black trace here shows essentially no diborane coming off of the sample. And so what we're showing here is that we can actually control the reaction pathway by incorporating it into these very small nano framework materials. And the figure on the right just indicates that we can reversibly hydride the material. So we can go back and forth between whatever the decomposition products are, and we can reform the lithium borohydride in these pores at relatively moderate temperatures and pressures. So that's a big step forward. What we've been doing more recently is playing with what's called the functionalization of the surfaces. So, functionalization is a fancy chemistry word for making the materials more reactive for something specific that you're interested in. And if you have a carbon framework, it's fairly easy to functionalize it, because if I look at a really small piece of the periodic table, I'm just showing what's to the left and to the right of carbon. I have two other elements. I have boron to the left and I have nitrogen to the right. And so if we look at the electron numbers for each of these atoms, boron has one less electron than a carbon atom, and nitrogen has one more electron than a carbon atom. So I can play some games with the number of electrons that are around the carbons if I can substitute either boron or nitrogen into these frameworks. So let me give you a very simple description of the two common notions of acids and bases. So many of you are probably familiar with the Bronsted acid. So hydrochloric acid, sulfuric acid, these kinds of acids are very obviously proton donors. And so proton donors are Bronsted acids and proton acceptors are Bronsted bases. The notion of acids and bases was generalized somewhat by a guy named Lewis. And he said that an acid is an electron acceptor. So this makes a lot of sense. If I'm donating protons, I'm giving away positive charge. It's kind of the same thing. I'm lowering my positive charge. How can I do that? I can do that by accepting electrons which have negative charge. So the other concept here is that Lewis acids are electron acceptors and Lewis bases are electron donors. So let's look at a Lewis acid, Lewis base complex. And this is a very simple example of one. I have BH3, which is borane, it's half of diborane, a BH3 molecule, and then I have an NH3 molecule, which is ammonia. And if I get these molecules close together, there's what's called a lone pair of electrons on the nitrogen atom. And this lone pair of electrons acts as a Lewis base. It can donate to the boron. And I can form, and it does donate to the boron, and I can form this complex, and this complex forms a molecule of ammonia borane. And this is sort of a basic example of a Lewis acid, Lewis base complex. Okay, now, if I put a nitrogen in my carbon framework, the question is, will it act the same way? And so what I'm showing here in the picture is a carbon sheet. So this would ostensibly be graphene. I've terminated the graphene sheet. So the green atoms are carbon. These little white atoms are hydrogens that terminate the sheet. And then I've taken out a carbon atom. I've created a vacancy in the carbon sheet. And I've replaced one of the atoms that's on the interior of this vacancy. I've replaced it with a nitrogen atom in blue. And if I want to look at where the electrons are in this material, I can do a specific kind of quantum mechanical calculation. It just tells me where the electrons are in the material. And what I'm showing here in the little inset, this is a molecule of pyridine. So pyridine is basically a benzene ring where you take one carbon atom and you replace it with a nitrogen atom. And if you do this quantum mechanical calculation, you can locate where the electrons are. And this blue bulb here is showing the electrons that form this so-called lone pair on the pyridine molecule. But you'll notice that in my carbon sheet, where that nitrogen is located, I have the same lone pair. So that means that I can utilize, that means that number one, that nitrogens in a carbon framework can act, they're called pyridinic because they can act like pyridine, and they can donate electrons to things that are in the vicinity of that nitrogen heteroatom. Okay, so my group did some work on this a number of years ago where we looked at another complex hydride. This has lithium, boron, nitrogen, and hydrogen in it. And at the time we were doing this work, we didn't necessarily intend to dope the material with nitrogen, but we did. And I don't have a lot of time to go through all of the details here, but this is a graph that shows the heat given off or taken up by a material. Yes? Was there a question or no? Sorry. It shows the material, whether the heat's given off or taken up by a particular material. And so this is to say whether we can determine whether or not a reaction is endothermic. You have to put energy in to make it go, or if it's exothermic, if it gives off energy when it does go. And so with this material in bulk, if you start to heat, this is the temperature on the x-axis going up. As you begin to heat the material, this material melts, and melting is endothermic. I have to put heat into it. So, and we get a down spike for this particular, for the melting. And then when the material decomposes, it goes, these peaks go up, so it's exothermic. That's for bulk material of this compound. If we put this in a nanoporous carbon, what we see is that the decomposition is actually endothermic. So we've changed the reaction enthalpy from endothermic to exothermic. And this is still a material of interest, but it's rather complicated, so we've moved on to other more easily studied systems. So let me finish with one final example with lithium borohydride. In this work, this was done just last year by one of my graduate students just down the road. We purposely made a nitrogen-doped carbon of fairly high nitrogen content, and we incorporated lithium borohydride into it. And so what we have, or at least what we think we have, is nitrogen in the pore walls. So if you can imagine looking down one of these cylindrical pores, the pore walls are lined with nitrogen heteroatoms, and these nitrogen heteroatoms can act as these Lewis acid-based complexes. And so lithium borohydride is composed of lithium, boron, and hydrogen, and when it decomposes, you get some borane that comes off of it, the BH3. And so just like in the ammonia borane that I showed you earlier, this BH3 will coordinate with the pyridinic nitrogens in the pore wall. And so what it does is it forms kind of a little stabilizing layer, because these BH3s are stabilized through the Lewis acid-Lewis base complex with the wall. So and to show you this result in a very simple graph here, if I have bulk lithium borohydride and I put it into just a pure bare carbon, there's an energy for activation for doing the decomposition of the material, and it actually drops a large degree when you infiltrate it into a nanoporous carbon framework. If you dope the carbon framework with nitrogen, or you functionalize it with the nitrogen heteroatoms, as I've described, then what you see is that energy goes back up. You increase it. And so you can, in fact, stabilize this particular metal hydride by putting it into a nanoporous framework. And so what we're doing is trying to explore these ideas to utilize other complex hydrides by either stabilizing them or destabilizing them and making them more useful and with properties that are more easy to engineer around and have all of the targets met for the Department of Energy. Okay, I have a couple of slides just to discuss, show you that the materials that we're preparing are also useful for battery-related materials. So this picture is just a coin cell, and these are commercial coin cells that you can purchase in the store. They're called 2032 cells. You've probably seen them at Walgreens or anywhere you go. And we can prepare coin cells like this using some of our materials. This is a copper sheet, and then we have some of our nanoporous carbons on the copper sheet. And we can we can either place lithium-ion active materials inside these nanoporous carbons, or we can use them as electrochemical capacitors. There's a lot of methods by which you can utilize these nanoporous frameworks. And I'll end on another slide here for batteries where we've incorporated nanoparticle titanium oxide, which is a material that's currently of interest for lithium-ion applications. And I've gone a little bit over time, I apologize, but I just wanted to show you some other applications for these materials. So with that, I'd like to just thank everyone for your attention, and please ask any questions. I'd be happy to answer them. Yes?
So as a system for running a car, you're producing all this produces electricity?
Yes, so the hydrogen would come off you would heat the tank, hydrogen would come off, you would utilize it in your fuel cell, and your fuel cell, when it runs, actually gives off a little heat because you're still combining the oxygen and the hydrogen, so you're getting a lot of energy out of that. And that waste heat you can use to generate more hydrogen from your hydride bed. Yes? Yes?
So as you are developing these materials, do they become patentable or not? I'm not sure when the particular applications you're using them for, is that patentable item or is that?
Yes, absolutely. So we have patents on a few of the different materials that we've produced. So much of it is the technique that you would use to make a framework or do a specific functionalization or somehow control some material property. Yes. Other questions? Yes.
Are you saying that someday H2O and O2 will be used as fuel in our cars?
Well, not directly, but once we take the water, we can electrolyze it, separate the hydrogen and oxygen, and then we can just store them separately. And then then we can use them on the vehicle in order to generate electricity. So yes, I mean in a sense, but yes.
Is the energy to separate them less than or equal to the energy you get when you combine them?
It's the same. It's reversible, yeah. So however much energy it takes to separate them, that's what you'll get back when you recombine them.
So you can have a coal burning plant to separate them?
Well, we wouldn't want to, that would generate lots of CO2, so we would like to just use solar or wind power, something renewable. Yeah. Yes?
Why isn't solar and wind power on a car enough to power a car instead of the hydro?
I think you can if the car is very light. So there are some solar powered vehicles. I think they have some engineering competitions for solar powered vehicles. But the cars typically have to be light. We like to drive big things here in the country. Sometimes our vehicles are quite large and very heavy, and so you need a lot of power. So 10 kilowatts, for example, to move a vehicle. So for that purpose, we need a lot of energy, and we need to store lots of energy, and so we can store that most efficiently in something like hydrides.
Because I was thinking that if you use a wind turbine as you're driving a car, the wind turbine will spin, and it'll create more electricity as you drive the car.
There's a catch there, though, because if you're driving the car to turn the windmill, you have to put the energy in. And then you would get the energy back with the wind resistance. So you'd be, you're kind of fighting yourself a little bit there. But yes.
You said it was for storing it. It was a 60 to 90% with using the hydrogen system.
Yes, PEM fuel cells are about 60 to 90%
Would the
efficient.
losses be from just losing some of the molecules then?
There's, like a battery, a fuel cell also has an internal resistance. And so you'll lose some of the energy in the resistive parts of the fuel cell. Yes?
Your last slide is about the battery technology, I think. You said titanium. Are you thinking of a replacement? The nano titanium might be a replacement for the lithium ion stuff, or did I read that entirely wrong?
No, there are many materials under consideration for both the anode and the cathode and lithium-ion batteries. So there's some quite exciting work actually in increasing the energy density of lithium-ion batteries. So right now, just to throw out a number, the number is about 170 milliamp hours per gram. So it doesn't mean a lot necessarily, but for some of the materials that are currently being researched now might have capacities, up to 10 times as high. So you can imagine having a lithium-ion battery that has, several days worth of capacity in it, and so on. But this is one material that we looked at for lithium-ion capacity, for lithium-ion batteries. But there are many. This lithium-ion research is probably is a much larger area of research actually because it's so commercially viable.
I have a quick question.
Yes.
Could this technology be applied to jets, planes?
Yes. In fact, Boeing at one time, and I think they are currently still interested in some kind of fuel cell technology for onboard electricity generation. So I think everyone probably heard of the battery problem that Boeing had with the lithium ion. I think I think they figured that problem out, but they're also interested in rather than just having lithium ion, but also having maybe some hydrogen fuel cells. But I don't know the details of their research operation.
Great, well, thank you again. That was
All right, thank you.